Here is something most people do not know about the Great Pyramid of Giza. Despite being the most studied building on Earth, despite thousands of years of exploration, 2 centuries of formal archaeology, and some of the world's most advanced technology pointed at it, scientists discovered a previously unknown hidden space inside it as recently as 2017. Not a small gap. A space the length of a 10-story building laid on its side. And the only reason we found it is that physicists figured out how to use cosmic rays from outer space as a scanning tool. So here is the question worth sitting with at the start of this story. If that much was still hidden after 4,500 years, what else might still be in there? For most of recorded history, there was only one way to investigate the interior of the pyramids. You had to go in. That meant chisels, hammers, blasting powder, narrow tunnels carved by hand through millions of tons of ancient limestone. The pyramid paid a heavy price for every secret it gave up. But here is what makes the last decade so remarkable and so quietly revolutionary. Scientists stopped going in. They started looking through, using particle physics, thermal imaging, laser mapping, and robotic cameras small enough to slip through gaps between stones sealed for millennia. What these technologies detected was not folklore, it was not wishful interpretation, it was measurable, peer-reviewed, independently verified data. And what that data revealed forces a simple but striking admission from even the most cautious Egyptologists. The internal architecture of the Great Pyramid is significantly more complex than everything documented before the 21st century. There are spaces inside that structure that no human being has ever entered, spaces that existed hidden through the entire span of recorded civilization. And the story of how we found them is, in many ways, more astonishing than the spaces themselves. When the most studied structure on Earth still surprises you, it is worth asking why. We tend to think of the Great Pyramid of Giza as solved, and on the surface, that confidence is understandable. The pyramid has been the subject of formal investigation for over 200 years. Yet its external dimensions have been measured to extraordinary precision. Its major internal chambers, the King's Chamber, the Queen's Chamber, the Grand Gallery, have been mapped, photographed and studied exhaustively. Tourists walk through it. Schoolchildren learn about it. Documentaries have covered it from every conceivable angle. And yet, in November 2017, a team of physicists and archaeologists published a paper in one of the world's most rigorous scientific journals, announcing something that stopped the research community cold. There was a void inside the Great Pyramid, at least 30 meters long, that had never appeared on any map, never been detected by any previous investigation, and never been entered by any known explorer in 4,500 years of history. The discovery did not come from a lucky dig, and it did not come from a translated papyrus or a rediscovered map. It came from muons, subatomic particles produced when cosmic rays collide with Earth's upper atmosphere, raining down through everything on the planet's surface, including 6 million tons of ancient limestone. To understand why that matters, you need to understand what the pyramid's history of investigation actually looked like, and why so much of it left so many blind spots. The earliest recorded forced entry into the Great Pyramid did not happen in the age of modern archaeology. It happened around 820 AD, when the Abbasid Caliph Al-Ma'mun ordered workers to tunnel directly into the pyramid's northern face. They did not know where the internal passages were. They simply hammered inward, hoping to find treasure. What they eventually broke through into was the descending passage. an existing corridor that had been sealed and hidden so effectively that it survived nearly 1400 years of attempts to locate it from the outside. Al-Ma'mun's team found the known chambers. They found no treasure, but what their mission proved, and what every subsequent intrusion over the following 12 centuries reinforced, was that the pyramid had been engineered with concealment in mind. Passages were offset. Entrances were hidden behind casing stones. Internal junctions were disguised. The pyramid was not simply a structure, it was a structure that had been deliberately designed to resist discovery from within. By the 19th century, European archaeologists and adventurers were investigating the pyramids with significantly more force. A Colonel Howard Vyse, working at Giza in 1837, used gunpowder to blast his way into previously inaccessible spaces above the king's chamber. He discovered 4 additional relieving chambers stacked above the one already known. He also found something else, faint red ochre markings on the stones, including what appeared to be a cartouche of the pharaoh Khufu. Those markings remain the only direct written evidence inside the Great Pyramid connecting the structure to any named ruler. They have been scrutinized, debated, and repeatedly verified. The Egyptian quarry workers who painted them almost certainly did so as work gang identifiers, a common practice documented at other pyramid sites. But their location, deep inside spaces that had been sealed since construction, it means they are as close to a contemporaneous signature as the pyramid has ever offered. And yet, even with those chambers blasted open, even with every known passage mapped, the pyramid still held a space 30 metres long that no one detected for another 180 years. The reason is straightforward, even if it took until the 21st century to solve it. Human investigators can only go where there is an opening. The Great Pyramid is not a hollow structure with rooms and corridors running through it like tunnels in a mine. It is an almost solid mass of approximately 2.3 million stone blocks, with a small network of passages and chambers occupying a fraction of its total volume. Any space that does not connect to a known passage, any void sealed completely by surrounding stone on every side, is, by definition, invisible to anyone walking through the pyramid's corridors. For 4,500 years, those sealed spaces simply did not exist as far as investigation was concerned, not because anyone was hiding them, but because the tools required to detect them had not yet been invented. That changed in the 21st century, and the instrument that changed everything was not a drill, or a camera, or a ground-penetrating radar system. It was a cosmic ray. The shift did not happen overnight. For most of the 19th and early 20th centuries, the dominant philosophy of pyramid investigation was essentially extractive. If you wanted to know what was inside a structure, you went inside it. And if the structure resisted, you forced the issue. While Howard Vyse's use of gunpowder at Giza in 1837 was not an aberration, it was standard practice for its era. The same logic drove investigators to chisel through blocking stones, widen narrow shafts, and remove original material to access what lay beyond. The information gained was real, so was the damage. Casing stones were stripped, interior surfaces were blackened by torch smoke. Structural joints that had remained untouched for thousands of years were disturbed by the weight of explorers and the vibration of blasting. Every answer extracted by force came with a cost paid by the monument itself. By the mid-20th century, that approach had become increasingly difficult to defend, not just ethically, but scientifically. Archaeologists were beginning to understand that context is data. The precise position of an object, the layer of debris surrounding it, the undisturbed relationship between adjacent stones, these details, once destroyed, could never be recovered. Invasive investigation was not just damaging the pyramids, it was permanently erasing the very evidence it sought to uncover. The question that slowly took shape across the field was a simple but radical one. Could you investigate a monument without touching it at all? The first was infrared thermography, a technology borrowed from engineering and materials science. Stone that is solid retains and releases heat differently from stone that conceals a void or air pocket behind it. By scanning the pyramid's surface with thermal cameras at dawn, as the structure heats unevenly after a cold desert night, researchers found they could detect temperature anomalies invisible to the naked eye. A difference of even a few degrees in a block's surface temperature can indicate something unusual behind it, a gap, a change in density, or a shift in material composition. The second was cosmic ray muon radiography, the technology that would ultimately prove most consequential. Muons are subatomic particles produced continuously in Earth's upper atmosphere as incoming cosmic rays collide with air molecules. They pass through almost everything, including solid rock, but denser material absorbs more of them. By placing muon detectors inside a pyramid's known chambers and measuring the flux of particles arriving from different directions, physicists can construct a density map of the stone above, effectively producing something functionally equivalent to an X-ray of the entire structure from the inside out. The third was three-dimensional laser scanning, a method that fires rapid pulses of laser light at interior surfaces and calculates precise distances from the reflection times. The result is a point cloud model of extraordinary accuracy, capable of revealing subtle misalignments, construction phase boundaries, and dimensional variations that manual measurement would miss entirely. The fourth was endoscopic robotics, small camera systems mounted on flexible or wheeled platforms, capable of navigating passages too narrow or too fragile for human entry. Where a shaft is only 20 centimetres wide and runs at a steep angle for 60 metres, a robot goes where an archaeologist cannot. The fifth was microgravimetry, the measurement of minute local variations in Earth's gravitational field. A hidden void has less mass than surrounding solid stone. That difference, though extraordinarily small, is detectable with sensitive enough instruments, and its location can be mapped spatially across a structure's footprint. None of these technologies require breaking anything. None of them leave a mark. Together they represent a complete inversion of the old logic. The pyramids stopped being excavated. They started being scanned. And what emerged when the scanning began was not confirmation of what archaeologists already knew. It was something else entirely. In October 2015, Egypt's Ministry of Antiquities did something that would have been unthinkable a generation earlier. Instead of commissioning an excavation, they launched a scan. The project was called Scan Pyramids. Its team was international. Egyptian archaeologists working alongside physicists, engineers, and imaging specialists from France, Japan, and Canada. Their mandate was precise: investigate the internal structure of 4 major Egyptian pyramids using exclusively non-invasive technology. No drilling, no removal of material, no physical intrusion of any kind. The Great Pyramid of Giza was the obvious starting point. The first technology deployed was infrared thermography, and the team ran their initial survey during the hours that maximize its diagnostic value, just after dawn, as the desert sun begins heating the pyramid's outer surface. A stone that has spent the night cooling releases that stored heat at a rate determined by its composition and what lies immediately behind it. Solid limestone of uniform density behaves predictably. Anything that deviates from that uniformity, a void, an air pocket, a cavity, a change in block arrangement, creates a measurable difference in the surface temperature directly above it. The cameras recorded the entire eastern face of the Great Pyramid as it warmed, and on that face, at the lowest courses of stone near the base, something unexpected appeared. Several blocks on the eastern side were registering surface temperatures significantly higher than the stones immediately surrounding them. The differential was not marginal. It reached approximately 6 degrees Celsius. In thermographic terms, that is not background noise. That is a signal. The explanation involves straightforward physics. Stone that borders an airspace, even a sealed one, loses heat overnight more quickly than solid stone, because air conducts heat far less efficiently than dense limestone. When the sun returns and heating begins, that same stone warms faster for the same reason. The result is a temperature signature at the surface that, to a thermal camera, effectively marks the boundary of whatever lies behind. The anomalous blocks on the eastern face were behaving as though something behind them was different from the surrounding structure. What that something was remained, at that point, entirely unknown. The thermal data alone could not determine depth. It could not resolve dimensions. It could not distinguish between a deliberate architectural void, a natural fissure, or a variation in construction fill. Infrared thermography identifies surface temperature differences. Interpreting what causes them requires additional investigation. But the significance of the finding was not diminished by that uncertainty. If anything, the uncertainty sharpened the attention of the team considerably. To appreciate why, it helps to consider what the thermal anomaly represented within the broader context of pyramid research. For well over a century, the working assumption among mainstream archaeologists had been that the Great Pyramid's internal structure was essentially fully mapped. The known chambers and passages, the King's Chamber, the Queen's Chamber, the Grand Gallery, the subterranean chamber, the ascending and descending corridors, had been surveyed exhaustively. Minor variations in stone quality and construction technique had been documented. There was no serious expectation that anything architecturally significant remained undetected. The 2015 thermographic survey introduced, for the first time in the modern era, measurable physical evidence that the pyramid's internal structure might not be fully accounted for. The eastern face was not behaving uniformly. Specific zones were responding differently to the same external temperature conditions. Something behind those stones, whether structural, spatial, or compositional, was altering the thermal signature of the surface above it. That finding did not answer any questions on its own. What it did was far more consequential. It proved that questions remained to be asked. And it sent the Scan Pyramids team back to the pyramid the following year with their most powerful instrument yet. One capable of seeing not just the surface, but straight through to the core. The thermal anomaly had pointed at something. Now the team needed a tool that could look directly at it. That tool had not been invented for archaeology. It had been developed by particle physicists studying the internal structure of volcanoes, and its operating principle depended not on any technology built in a laboratory, but on a process happening continuously, invisibly, across the entire atmosphere above Earth's surface. When high-energy cosmic rays, streams of charged particles originating from sources across the universe, collide with molecules in Earth's upper atmosphere, they produce cascades of secondary particles. Among these are muons, subatomic particles similar in some respects to electrons, but significantly more massive and capable of penetrating extraordinary depths of dense material before being absorbed. At sea level, billions of muons pass through every square metre of Earth's surface every hour. They pass through buildings, through soil, through water, and through stone. They pass through human bodies continuously without effect or detection. But they do not pass through everything equally. Denser material absorbs more muons. Less dense material, or empty space, allows more muons to pass. The difference in the number of muons arriving at a detector from any given direction is therefore a direct measurement of the density of whatever lies along that path. Place a muon detector inside a known chamber within a large stone structure, record the flux of particles arriving from every angle over a sufficient period of time, and you can construct a density map of the entire mass of stone above and around you without touching a single block. This is muon radiography, and by the time the Scan Pyramids team deployed it at Giza, the technique already had a significant track record. In 2007, Japanese physicists used muon radiography to image the internal structure of Osama, an active volcano in central Japan. The resulting density maps revealed magma pathways and internal cavities that no physical investigation could have safely accessed. The data matched subsequent geological findings with high accuracy. The same principle has been applied to nuclear reactor inspections using muon scattering to assess the condition of reactor cores without dismantling containment structures. In both cases, the technology demonstrated a consistent and verifiable ability to detect density differences inside massive, impenetrable objects. The Great Pyramid presented a similar challenge in structural terms. An enormous mass of material with known internal spaces and potentially unknown ones. The question was whether the muon flux data collected from inside its chambers would reveal anything beyond what was already mapped. The Scan Pyramids team did not rely on a single detection method. To ensure that any significant finding could be independently verified, they deployed 3 separate muon detection systems simultaneously, each operating on a different physical principle. The first used nuclear emulsion plates, sheets of photographic material that record the tracks of passing muons with exceptional spatial resolution. These plates were left in position for extended periods and then chemically developed and analysed. The second used scintillator hodoscopes, detectors that produce a flash of light each time a muon passes through, allowing real-time tracking of particle trajectories and the continuous accumulation of directional flux data. The third used gas detectors, chambers filled with specialised gas that ionises when a muon passes through, generating an electrical signal that records the particle's path. 3 different technologies, 3 independent data sets, 3 separate teams of physicists conducting their own analyses. All 3 reached the same conclusion. Above the Grand Gallery, in a region of the pyramid that every previous map had marked as solid stone, there was an anomaly in the muon flux too large, too consistent, and too clearly defined to be anything other than a significant void. For the first time in 4,500 years, humanity could see through 6 million tons of ancient stone, without a single drill, without a single gram of explosive. The next question was what exactly they were seeing. On the 2nd of November 2017, the journal Nature published a paper that immediately reordered the conversation around one of the world's most studied monuments. Its title was precise and deliberately restrained: Discovery of a Big Void in Khufu's Pyramid by Observation of Cosmic Ray Muons. Yet the language throughout was careful, methodical, and exactly what peer-reviewed physics demands. But the finding it described was anything but routine. Above the Grand Gallery, the pyramid's most architecturally distinctive internal feature, a corbelled ascending corridor nearly 9 metres tall and 47 metres long, the 3 independent muon detection systems had identified a void of extraordinary dimensions. The space was estimated to be at least 30 metres long. Its cross-sectional profile, based on the muon flux patterns recorded from multiple detector positions, appeared broadly similar to that of the Grand Gallery itself, suggesting a large elongated cavity rather than a narrow crack or a small pocket of loose fill. It sat directly above the Grand Gallery and in a region of the pyramid's interior that had appeared on every architectural map since the 19th century as uninterrupted solid stone. The research team was explicit about the confidence level of their finding. The anomaly was detected independently by all 3 detection systems: the nuclear emulsion plates, the scintillator hodoscopes, and the gas detectors, each analysed by a separate team working from its own data set. The probability of all 3 producing a coincidental false positive of this magnitude and in this precise location was, in statistical terms, effectively 0. This was not an artifact of the equipment. It was not a calibration error. It was not ambiguous data interpreted optimistically. It was a void, large, real, and previously completely unknown. The announcement was careful to avoid the word chamber. That distinction matters. A chamber implies a room, a defined architectural space with a deliberate purpose, potentially containing objects, inscriptions, or features of direct historical significance. The muon data confirmed that a large empty space exists. It did not and could not determine what that space looks like in detail, whether it is accessible from any existing passage or what function it was intended to serve. The interpretation that has gained the most traction among Egyptologists, and the one most consistent with documented Egyptian engineering practice, is that the void functions as a structural relieving space. The principle is already visible elsewhere in the same pyramid. Above the king's chamber, 5 successive chambers were constructed during the original build, not as rooms with any ceremonial purpose, but purely to redistribute the enormous compressive load of the stone above, protecting the ceiling of the chamber below from fracture. The pyramid's builders understood, in practical terms, the mechanics of load distribution across massive stone structures. The Grand Gallery is the longest and tallest internal span in the pyramid. It is precisely the kind of structural feature that would generate significant downward pressure on the stone beneath it. A relieving void positioned directly above it, reducing the mass pressing down on the gallery's roof, would represent a logical and sophisticated engineering response to that problem. If that interpretation is correct, the void is not a hidden room waiting to be entered, but it is evidence of structural ingenuity more advanced than anything previously documented in the pyramid's known architecture. Either way, the significance of the 2017 finding cannot be understated. The last confirmed major architectural discovery inside the Great Pyramid occurred in 1837, when Howard Vyse blasted his way into the relieving chambers above the king's chamber. 180 years passed, and then a team of physicists using subatomic particles and photographic plates found something larger than anything Vyse had uncovered, without removing a single stone. The pyramid had held that secret for 4,500 years. It had simply been waiting for the right question to be asked in the right language. The big void had been detected, but detection, by itself, leaves a fundamental question unanswered. Muon radiography measures density differences. It confirms that something is there. It cannot show you what that something looks like, its surface texture, its construction, the relationship between its walls and the blocks surrounding it. For that, you need eyes inside the space itself. In 2023, for the first time since the Big Void announcement, researchers achieved exactly that. Not above the Grand Gallery, but in a location that made the finding even more disorienting. It was at the entrance. The original northern entrance of the Great Pyramid is not an obscure or difficult to access feature. It sits on the pyramid's northern face, approximately 17 metres above ground level, and has been the primary access point for investigators since at least the 9th century. Every archaeologist, engineer and explorer who has ever entered the pyramid has passed through or immediately adjacent to it. Above that entrance sits a distinctive architectural feature, a pair of large limestone blocks arranged in an inverted V-shape, known as chevron blocks. Their function has been understood in general terms for some time. The angled arrangement deflects the compressive weight of the stone above the entrance away from the corridor below, preventing the ceiling from being crushed under the load of the pyramid's upper courses. Similar chevron configurations appear elsewhere in Egyptian architecture, wherever a void or opening needed to be protected from overhead pressure. Yet what had not been known, what no survey in the long history of the pyramid's investigation had detected, was what lay immediately behind them. Using a combination of preliminary scanning and a small endoscopic camera inserted through a joint between stones, the research team confirmed the existence of a previously undocumented corridor running behind the chevron blocks. It was approximately 9 metres long, roughly 2 metres wide, and constructed with the same precision evident throughout the pyramid's known internal architecture. The corridor had not been discovered by accident. Scanning had identified an anomaly in the structure above the entrance, and the endoscopic insertion was a targeted response to that data, a minimal, non-invasive physical confirmation of what the instruments had suggested. The images returned by the camera were unambiguous. This was not a natural gap between imperfectly fitted stones. It was a built space. Defined walls, deliberate geometry, intentional construction. The leading interpretation positions the corridor as an additional stress distribution feature, a spatial buffer designed to further reduce the load bearing down on the entrance passage below. The chevron blocks above the entrance handle the immediate overhead pressure. The corridor behind them may represent a secondary relieving measure, ensuring that the structural forces generated by millions of tons of stone above are dispersed across a wider area before reaching the corridor ceiling. This would be entirely consistent with what the pyramid's engineering, as understood through both the known relieving chambers and the likely function of the Big Void, increasingly suggests that its builders had a far more sophisticated grasp of internal load management than early archaeology gave them credit for. What makes the 2023 discovery particularly striking is not its size. 9 metres is modest compared to the 30-metre Big Void above the Grand Gallery. What is striking is where it was found. Not deep in an uncharted region of the structure, not in a remote shaft or an inaccessible upper course, but directly behind the entrance, the single most examined, most photographed, most studied point of access on the entire monument. Investigators had been walking past it for centuries. The corridor had been there the entire time, sealed behind stone that no one, until scanning technology made it visible, had any reason to look through. If the entrance zone was not fully mapped, after 4,500 years of investigation, the question that follows is an uncomfortable one. what else remains undetected further inside? The hidden corridor confirmed something that the Big Void had only implied. The pyramid's builders were not simply stacking stone. They were engineering interior space with a level of deliberate precision that modern investigation is only beginning to fully account for. And nowhere is that precision more quietly remarkable or more persistently puzzling than in the narrow shafts that run from the Queen's Chamber deep into the pyramid's core. The Great Pyramid contains 4 narrow shafts, 2 originating from the King's Chamber and 2 from the Queen's Chamber. Now, those from the King's Chamber connect to the pyramid's exterior. Those from the Queen's Chamber do not. They run upward at steep angles for approximately 65 metres before terminating against blocking stones, completely sealed within the body of the pyramid. For most of the 20th century, these shafts were classified as ventilation ducts, a functional explanation that satisfied investigators who noted their roughly north-south and south orientations and assumed they served the practical needs of construction workers. That explanation has not survived closer examination. Ventilation ducts do not need to be sealed at both ends with precisely fitted limestone blocking stones. They do not require copper fittings embedded in those stones, and they are not typically aligned, as independent researchers and archaeologists have noted, with a degree of astronomical precision that places them in direct orientation with specific stars visible from Giza during the pyramid's construction period, including Orion's belt to the south and the circumpolar stars to the north. Whatever these shafts were designed to do, the evidence suggests it was intentional, specific, and sealed from the moment construction was complete. In 1993, German engineer Rudolf Gantenbrink sent a small tracked robot called Upu-Out 2 into the southern shaft of the Queen's Chamber. A passage just 22 centimetres wide, running at an angle of approximately 45 degrees. The robot travelled 63 metres before its camera transmitted an image that stopped the research team mid-session. At the shaft's terminus, blocking the passage entirely, was a fitted limestone slab, where protruding from its lower edge were 2 copper fittings, small, looped and deliberately attached. They resembled, in function, if not in scale, the kind of hardware used on doors throughout ancient Egyptian architecture. The find was immediately significant. A sealed shaft terminating in a fitted stone with copper fixtures is not the endpoint of a ventilation duct. It is the endpoint of something that was meant to be closed. In 2002, a subsequent robotic mission drilled a small hole through the limestone slab and inserted a fibre optic camera. What it revealed on the other side was not a chamber, not an inscription, and not a connecting passage. It was another blocking stone, a second slab, positioned a short distance beyond the first, sealing the shaft at a second point. And a further robotic investigation in 2011 used a camera system capable of looking sideways through the drilled hole at an angle, revealing that the rear face of the first blocking stone carried markings, red ochre symbols similar in character to the quarry marks found elsewhere in the pyramid. Their meaning has not been determined. Their presence confirmed again that someone had handled these stones deliberately and with evident purpose before sealing them in place. Taken together, the evidence from the Queen's Chamber shafts points to a consistent conclusion. These were not incidental features of construction. They were engineered pathways, built to precise angles, oriented with astronomical care, terminated with fitted blocking stones and copper fixtures, and sealed completely before the pyramid was finished. A modern robotic scanning continues to study these shafts without further physical intrusion. The 2011 mission remains the last direct investigation. What lies beyond the second blocking stone in the southern shaft has not yet been determined. The pyramid, in this respect, as in others, has not finished withholding. Everything examined so far has focused on a single structure, but the Great Pyramid of Giza did not appear fully formed. It was the product of a construction tradition that spanned generations, one that involved failure, correction, and progressive refinement on a monumental scale. And when modern scanning technologies were turned on the pyramids that preceded and surrounded it, what emerged was not a collection of isolated monuments, but a legible record of an engineering culture learning from its own mistakes in real time. Approximately 40 kilometers south of Giza, at the site of Dashur, stands the Bent Pyramid, built by Pharaoh Sneferu, Khufu's father, and almost certainly completed before the Great Pyramid was begun. Its defining characteristic is visible from a considerable distance. Roughly halfway up its height, the pyramid's angle changes sharply, from a steep incline of approximately 54 degrees at the base to a shallower angle of around 43 degrees above it. The result is the distinctive bent profile that gives the structure its name. For decades, the dominant explanation was that the builders, alarmed by structural problems developing during construction, possibly cracking in the internal chambers, detectable even as work continued, made an emergency decision to reduce the angle and lower the final weight of the structure. Scan pyramids, muon radiography data collected from the Bent Pyramid between 2015 and 2019 added significant detail to that picture. The scans revealed internal density variations, consistent with stress responses in the lower section of the pyramid, areas where the stone arrangement shows evidence of the structural pressure that likely prompted the angle change. They also identified previously undocumented internal features in the upper section, where the shallower angle creates a different load distribution pattern than the base. The Bent Pyramid is not a failed pyramid. It is a pyramid that was corrected mid-construction by builders who understood in practical terms that something needed to change, and changed it. Sneferu's next pyramid, the Red Pyramid, also at Dashur, maintains a consistent angle of approximately 43 degrees from base to apex. That is precisely the shallower angle adopted for the upper section of the Bent Pyramid. The implication is direct. The builders took what the Bent Pyramid's correction had taught them about stable incline ratios and applied it from the foundation of the next structure. Scanning of the Red Pyramid has confirmed a more uniform internal density profile than its predecessor. The structural irregularities that characterize the Bent Pyramid's lower section are absent. The internal chambers, while simpler in configuration than those in the Great Pyramid, show evidence of the same chevron block weight distribution logic seen above the Grand Gallery and the northern entrance at Giza. The Red Pyramid represents a successful implementation of lessons learned one monument earlier. Khafra's pyramid at Giza, built immediately after the Great Pyramid by Khufu's successor, presented a different set of questions for the scanning teams. Its internal layout is simpler than Khufu's, with fewer passages and chambers, but three-dimensional laser scanning and density analysis have revealed subtle construction phase variations within the structure, evidence of planning adjustments made as building progressed, and of a workforce operating with the accumulated knowledge of multiple previous construction projects. And across these three pyramids, a pattern emerges that no single structure could reveal on its own. Pyramid construction was not an event. It was a process, iterative, responsive, and improving across successive reigns. The scanning data shows builders who encountered structural limits, identified them, and incorporated the lessons into subsequent designs. The pyramids, viewed together through the lens of modern scanning, are not monuments to mysterious capability. They are the documented output of an engineering tradition that got progressively better at what it was doing, and left the evidence of that progression sealed inside stone for 4,500 years. It is worth pausing at the end of this account to take stock of what has actually been found. Since the Scan Pyramids project launched in 2015, a non-invasive technology has confirmed a thermal anomaly on the eastern face of the Great Pyramid, detected a void at least 30 metres long above the Grand Gallery, physically verified a previously unknown corridor behind the northern entrance, and added significant structural detail to our understanding of the Bent Pyramid, the Red Pyramid, and the Pyramid of Khafra. The sealed shafts of the Queen's Chamber remain only partially explored. Internal density maps of all four pyramids continue to be refined. New scanning campaigns are periodically proposed, approved, and conducted. This is an active field. The investigation is not complete. Clarity about what scanning has revealed requires equal clarity about what it has not. No hidden treasure chamber has been confirmed inside any of these structures. No inscriptions have been detected in the Big Void or the 2023 corridor. No evidence has emerged to suggest that the pyramids were built by any population or civilization other than the ancient Egyptians, whose administrative records, worker settlements, tool marks, and quarry inscriptions surround these monuments on every side. The scanning data has not rewritten history. It has not overturned the foundational chronology of Egyptian archaeology. It has not produced findings that require any revision to the established understanding of who built the pyramids, when, or in what social and political context. What it has done is more specific, and in many respects more interesting than any of those things. There is a tendency to assume that demystification diminishes, that understanding a thing makes it smaller. What the scanning record of the pyramids argues precisely the opposite. Before muon radiography, before thermography, before robotic endoscopy, Egyptologists knew that the Great Pyramid contained relieving chambers above the King's Chamber, a sophisticated engineering solution to a significant structural problem. That knowledge was already impressive. What scanning has added to that picture is a monument whose internal stress management systems are now understood to be considerably more extensive than previously documented. A massive void redistributing load above the Grand Gallery, a corridor behind the entrance performing a similar function in a different zone of the structure, seal shafts engineered and oriented with a precision that goes far beyond any functional construction requirement. And yet the pyramid's builders were not working intuitively. They were solving specific structural problems with specific architectural responses, and doing so at a scale and with a consistency that the scanning data is only now making fully legible. Muon radiography, in its current form, can confirm the existence of a large void. It cannot yet resolve the internal geometry of that void in fine detail, map its surface features, or determine whether it connects to any other space within the structure. That resolution limit is a function of current technology, and current technology is improving. Higher density muon detector arrays are under development, capable of producing three-dimensional density reconstructions with significantly greater spatial precision than the systems used in 2017. Our artificial intelligence tools are being applied to existing muon flux datasets to extract structural detail that initial analysis did not capture. Micro-drone platforms, small enough to navigate the Queen's Chamber shafts without physical alteration to the stone, are in active development. What happens when those tools are brought to bear on the spaces already detected, and on the portions of the pyramid's interior that no detector has yet examined in detail, remains genuinely open. The second blocking stone in the southern shaft of the Queen's chamber has not been passed. The full dimensions of the big void have not been resolved. The purpose of the 2023 corridor has not been confirmed. For 4,500 years, the pyramids were opaque. Today they are becoming transparent, not mythically, scientifically, and the process, by every available measure, is far from finished.